We will learn how FlashAttention optimizes Softmax so it takes less memory in your GPU to calculate this Softmax, and you can fit and train your LLM faster, and transformers you can train faster. We have a block of code that shows traditional FlashAttention. So FlashAttention is also good at speeding up, and I always wanted to understand this, so let's see. We have this Q matrix. Ki is key matrix block of iteration I, which is block n and dimension. Okay, so they are dividing key matrix to blocks and value matrix as well. Actually, if you go to my channel, you can see these tutorials where we code some here in the Triton. Here, Triton matrix multiplication. I explained that well. And then accumulator for scores, we explained that as well. So result of Q times this K block, and it's gonna be block M, block N. So I guess M is the dimension of Q, and N is the dimension of the key, the K. Then we have these scores max, current max logits per query row. So I guess these are just logits, and they have this per query for each query, just logits. And then score scale factor to stabilize softmax computation, also block M. So it's just maybe dividing or scaling this, normalizing these scores, and then accumulating output, running attention output for each query row. So after we calculate attention, we just have it for each row of the query. We have the whole dimension, which is the whole like embedding vector for the query times, it's size query, but size query is same as size key, same as value. So I guess this is and then we have this blockwise loop. So for I, in range of how many blocks the matrix is divided into, we compute entire query matrix times block of the key, or matrix multiply block. Compute attention loggage for current block. And then score max previously is gonna be score. We save the previous scores into this variable, so we can use this variable to save new scores. So scores max, compute row-wise max for numerical stability. So we just find the maximum score in accumulated scores. We just find the maximum score, and then we calculate the scale, compute scale factor for previous output. So we say previous scores minus scores max. Okay, we compute the scale, and then we exponentiate here. I think this is just to remove dividing with 0 or something. I'm not sure why we exponentiate though. We can see. So calculate how to scale the previously computed attention output to match the current shifted softmax. This is part of the trick to incrementally compute softmax across multiple blocks. So let's see why we have this exp here again. Softmax with stability trick. Normally softmax is computed as exp of xi over all of the sum of all of the xi's or xj, so the sum of the entire array. So you have an array, you divide each number in the array with the sum of all of the numbers. But to prevent overflow, underflow from large exponentials, we use log sum exp trick. So what can happen is if you have this number to be very big, then exponentiating to this number will create a very big number that will not be able to fit into float 16 memory variable. So it will cut or become infinity, or there will be underflow, overflow, or underflow as well. It can become maybe minus infinity or none if this number is so small that the result cannot be represented. So if they actually subtract the maximum value of the array from every element, then if we have very big elements in the array, then they will just get scaled down. And so you will no longer have huge numbers here, so because the bigger the number, the more it will be scaled down. But this trick also helps with negative numbers, but I found a case where it doesn't really work, I think, but it still helps in some ways. So you see, if we have this array, minus 1000, minus 1001, minus 100,002, whatever, I just had a huge number at the end. Then if we calculate exp, all of them will get at 0 because the values will be so small that FP16 cannot represent them. So you see here, FP16, even of 100, it's almost not possible to represent. Although I don't know if this is... I guess it's correct. Okay. Anyways, it's so small. And all of them are zeros. So if we add all of the 3 zeros, then we have division by 0, which will give us none, none, none. So if we take maximum, which is minus 1000, then we will actually get 0 here, minus 1 here, and minus 99, whatever, it doesn't matter. So it fixes our problem, division by 0. So we will still actually have underflow here, but at least we don't have problem with division by 0 anymore. And if the difference between these scores is not this crazy, I made it very crazy, but I guess usually it wouldn't be this crazy. Usually these numbers would be similar. So we wouldn't even get underflow here usually, I believe. Like maybe this number would be similar to these numbers as well. But now we have this vector. So that's the trick. So in FlashAttention, you are computing attention block by block. That means you can't compute softmax over the whole thing at once. You want to compute the attention output incrementally while still being numerically stable. So as I said, we have this trick to prevent these nones, but we cannot subtract maximum from the entire sequence here because we are computing it in blocks. So we need to use some different trick. In FlashAttention, you only see some parts of x values at a time. So let's say you already seen some scores and built up an output, accumulated O output. Now you see new scores and want to add their softmax weighted values to accumulated output. But the new scores might have a larger max value than before. What does score scale is equal to exp scores max previous minus scores max do. Let's say previous is max value is 10 and the current one is 12, so it's higher. So your previous accumulated output was computed using a softmax shifted by 10, but now you're using a softmax shifted by 12. So you need to rescale the old output to match the new frame of reference shifted by 12. So the old softmax was exp x minus 10, new frame wants exp x minus 12, which is equal to exp x minus 10 times exp 10 minus 12. Yeah, this is mathematical trick, I like this. So you see, you have e to the x minus 10 times e to the minus 2. And you know, in mathematics you can combine. If you have this multiply, you can just put it all to the same e to the x minus 10 minus 2, which is e to the x minus 10, or minus 12, sorry. So we just need this part, because we already have this part, so we need this part, which is going to be our exp score previous max previous minus scores max. And then we will multiply this part with our scores scale, this guy. Here we have accumulated output times, so we just times it with a scores scale. So this line is rescaling the previously accumulated output to match the new softmax frame of reference. So as I said, it could have been computed with scale 10, but new scale is 12. So this is the problem, because the new block has a scale 12. So we cannot just add them, like concatenate them. We need to rescale accumulated output to also use minus 12 as a scale. So that will rescale it, this exp just as I said. So let's see on some numbers. Let's say we have scores 9, 10, and 8. And see, 10 is maximum. Then we do the softmax. So we will do the trick subtracting 10 from everything and then exponentiate and get these numbers. So it says here this is a softmax unnormalized. Let's just look at it as this. So it's not divided by this, each of them is not divided by the sum of the entire, but it doesn't matter for now. Let's ignore that. So we have these numbers, and let's see what we do in the FlashAttention. So let's suppose these are values. You know, when we have queries and keys, we get these numbers here, these scores with queries and keys. So let's say we also have values. So now weighted sum of the values, we take value times corresponding score plus second value times second score, etc. So I guess this is the output. Weighted sum of values is this one. So that's going to be initial accumulated output. So then let's say we have a second block. So query matrix times key, but the second block. So we get these scores. Now maximum is 12. Okay, so now the score scale, it's gonna be, first of all, it's gonna be this minus 2, because later we will multiply our output, which was the previous one, times the current scale to get the new scale. As I said, we use the mathematical trick. If we already have exp of 10, then if we multiply that with exp of minus 2, so we have minus 10 and minus 2, then we get exp of minus 12, which should be our new scale. I explained that trick like 5 minutes ago in the video. So we will just multiply our output from here with this new scaling factor to get the new output. So now this is the output for the previous block with this just scaling factor. So we need to now also calculate the softmax of the block 2 as well, and then add that. You see here we are at this step where we just take the current accumulated output and multiply with the scaling factor to rescale the previous output, but we still did not add the softmax of the current block. So that's gonna be second. So apply softmax shift trick to current logits. So we have accumulated I guess score or scores, yeah, of the current scores, and we just do the same. So scores minus maximum value and then exponentiate. So this is how we get the list of scores for the current block, and then we multiply that with the values matrix and just add that number to the accumulated output, which has been scaled properly now. So I guess that's it. So just to repeat the continue, so after we scale this accumulated output, old one, Then we calculate, so I'm just repeating what I just said in the code, I'm showing you the numbers. So we calculate this unscaled, in this case it's unscaled softmax, by just exponentiating this new block after subtracting the maximum value. And then we multiply these scores and the values for the second block, and then we do the weighted sum. So in the end, final step, we just add the old one that's rescaled to fit the new scale and the new accumulated sum, and get the new sum, and that's it. So we just got one number as a result, but in practice you would see a vector. So let's say you have two queries. We just had one query, but let's say you have two queries, and each has dimension 3, which is a vector of 3. Right now we just had like one number. So then accumulated scores would be 2 times block size of the key, and then output would be 2, 3, which is the size of the query and dimension of query. Each iteration you do exactly the same math, but on 2x3 matrix instead of a single number. So then accumulated output might look something like this. This is the entire like value times query times key softmax attention for this token, and then for this token. But right now in our example we just use one token that has one number as a vector embedding.